Hi students, so this is the lecture for Chapter 7. Now, normally in class I usually take 2 or 3 class periods to get through one chapter. For the online recordings, what I've decided to do is just lecture the entire chapter. It might be like a 2-hour lecture. I haven't practiced it and timed it out, but I'm assuming it'll turn out to be about 2 hours. I encourage you, if you want, depending on your style, if you'd like to watch the whole lecture the whole way through the first time and then maybe rewatch it later a second time to go through it a second time, that's fine. If you choose, you can watch it, to pause it somewhere in the middle and then resume watching it another day. That's fine as well. Depending on your pace and your learning style, it's pretty flexible in that way. But just wanted to let you know that this is going to be longer than a one class period lecture, both online as it would be in the classroom. So that being said, Chapter 7 is all about solution chemistry. It's all about solutions, about what they are, what is the definition of a solution, what are the parts of a solution, different types of solutions, how to write chemical equations for solutions, and then there is quite a bit of math in terms of calculating concentrations of solutions and being able to do dilutions, taking a concentrated solution and diluting it down to a less concentrated solution, and how to do that specifically, mathematically. So there is some math again in this chapter, and I will be working some problems with you still. And most of it, though, is all about unit conversions. So again, I stress, if you have your unit conversions down, you should be very successful. And then the last part of the chapter goes through osmosis and diffusion. Sort of the ultimate point of learning about solutions and their concentrations is because most of the fluids in our body is more than it's 50 to 70% water. But it's not really pure water. It's an aqueous solution, a solution of different nutrients and waste products dissolved in that water. So our body has a lot of solution chemistry going on, and most of it is involved in fluid balance and electrolyte balance. So the point of learning all this basic chemistry about solutions is to get a better understanding of osmosis and fluid and electrolyte balance in the body. So that's how we sort of close out the chapter. So what is a solution? Well, a solution is a mixture, and the example that the book opens up with is iced tea. Iced tea is a solution because it's a mixture of water and caffeine and sugar and some other things. So my question to you, is iced tea a homogeneous mixture or a heterogeneous mixture? Right, it's a homogeneous mixture. Well, actually, this is kind of a trick question. I'll pose this 2 different ways. The tea itself is a homogeneous mixture because the water, the caffeine, the sugar, it's all those phytochemicals, they're all mixed together, and you can't really see the different particles. If you throw ice in the glass, though, then you turn it into a heterogeneous mixture, right? Because the ice definitely does not evenly distribute within the glass. So tea is a homogeneous mixture. With ice in it, it would be a heterogeneous mixture. That's my interpretation. But anyway, the point is that the tea itself is a homogeneous mixture or a homogeneous mixture, and all of these particles dissolve, the sugar and the caffeine all dissolve in the water that is the main component of that solution. So a solution really can be broken down into 2 parts. It can be broken down into the solvent, and it can be and the solute, or sometimes there are multiple solutes, like in the case of the tea. So the solvent is whatever material is present in a larger quantity. So in this example here, we're making sugar water. So You have a whole bunch of water and like a spoonful or a couple spoonfuls of sugar. You stir them in to make a sugar solution. The solvent is the water because it is present in a larger quantity, whereas the solute is present in a smaller quantity. If we had sugar and salt in here, then we'd have two solutes, but still they would both be solutes because the solvent is the one that's in the largest quantity. Okay? So there are some distinguishing features of solutions that make them sort of a special type of homogeneous mixture. Because they're homogeneous mixtures, the particles are evenly distributed, and because they're mixtures and not chemical reactions, there's no chemical reaction occurring. It's just a mixture. But here's one of the sort of the defining characters of a solution is that the solution is transparent. You can see through it. Light passes through it. So iced tea, it's colored, but you can still see through it, just like water. It's transparent. Solutions, you can alter the concentration of solutions. That's something that's a property of a solution. And the thing that's going to separate solutions from a couple of other homogeneous mixtures we're going to talk about is this one here. That a key thing about solutions is that the components do not separate with time. That once they are dissolved in each other, they stay that way, can stay that way indefinitely, unless you do something physically to purposely separate them. So, just to make you aware, all solutions are not things dissolved in water. Most solutions that we think about are that way, and most of the solutions we'll talk about in the class focus on some kind of solute dissolved in water. These are called aqueous solutions, aqueous meaning water, a water solution. And the reason we'll focus mostly on aqueous solutions is because those are the solutions in our body, all the solutions within our cells, in our blood. Water is the major solvent in our bodies, so it's the one that we will focus on. But just wanted to mention that there are lots of other types of solutions. You can have other types of solids and liquids mixed together, but pretty much any state of matter you can mix all kinds of different types of matter. So you can have a gaseous solution of two different types of gases. In fact, the air that we breathe is a gaseous solution of nitrogen and oxygen and hydrogen, etc. You can have a gas and a liquid. A good example that we'll be talking about is soda, like carbonated beverages. You actually have gas, carbon dioxide, dissolved in the liquid beverage. Some other ones I want to point out. Solid and two different solids in a solution. Different types of metals are solutions, like metal alloys. Those are the ones I really wanted to sort of call out. But just be aware that there's other types of solutions. And there will be a couple of problems where we, illustrate that. Coming up right here. So our first practice problem from the book. Identify the solute and the solvent and solutions composed of the following. All right, so first of all, a little reminder, which is the component that's present in smaller amounts, the solute or the solvent? The solute. The solute is present in smaller amounts, okay? So I'm going to put a red square as we answer these questions. Which one of these is the solute? 0.8 liters of nitrogen, that when you mix 0.8 liters of nitrogen with 0.01 liters of carbon dioxide. Correct, the solute is going to be the carbon dioxide because it's in a smaller amount than the nitrogen, which would be the solvent. Next one, 3 tablespoons of vinegar or acetic acid mixed with 1 cup of water used to make a salad dressing. So here we have a liquid and a liquid solution. So which one is the solute? The solute would be the vinegar, right? Because 3 tablespoons is less than 1 cup of water. Lastly, 90% gold and 10% nickel. It's actually how you make white gold. My wedding ring, wedding bands, white gold. Alright, I think it's probably this combination or something similar. 90% gold, 10% nickel. Which is the solute? It's going to be the nickel. Okay? And that is an example of a solid and a solid type of solution. So you can see the different types of solutions that we have. Very good. Alright. So a solution, remember, two of the key things about solutions were that it was transparent and also that the particles don't fall out over time, don't separate over time. Colloids and suspensions sort of violate those rules. So they are homogeneous mixtures where everything is distributed, all the particles are distributed evenly throughout, and it looks homogeneous, but it's not clear, and or particles can fall out of suspension. So a colloid is a solution where the dissolved particles stay, they don't separate over time, they stay in the mix, in solution, I guess you could say, but it's not transparent. Whereas a suspension, the particles will fall out over time because they're larger. So some examples here, in a colloid, the reason that it's not transparent is because the particles are bigger, and so they block light. So if a suspension, or if a solution, I guess, has particles that are between 1 and 1,000 nanometers in diameter, then it'll stay in solution, but it also blocks light coming through it. So that defines it as a colloid. It's not transparent, but the particles do not settle. All right, and milk is an excellent example. There's these big protein and fat globules that kind of are permanently suspended, but also block light and make it opaque. A good example of a suspension would be your blood. If you withdraw blood from your veins, it looks homogeneous. It looks like an even mix of, red blood cells and liquids. But it's actually made up of a number of different components, including those red blood cells. So if you spin it down, you'll see those different components separate out. But if you don't spin it down, if you just leave it sitting in that tube for a couple of days, it'll naturally separate out into these different components. The red blood cells are heavy, they're large, they will actually settle to the bottom of the tube, whereas the plasma, the water, the actual solution component of the blood will remain on top. So a suspension is defined as a solution or a homogeneous mixture that has particles that are greater than 1,000 nanometers in size, or 1 micrometer. One micrometer equals 1,000 nanometers. So if the particle is that big, it will separate out given time, and therefore defines it as a suspension. So here's a quick sample problem. Are the following examples, are they solutions or are they colloids? A, apple juice, solution or colloid? Yes, solution. It's transparent. All of it doesn't settle over time. B, mayonnaise, solution or colloid? Mayonnaise would be a colloid. It does not settle over time, but it is not transparent. It is an even mixture, though. And C, this trickiest one, is fog. Is fog a solution or a colloid? Remember, ask yourself 2 questions. Is it transparent? And does it settle over time? Or I guess in this case, we're not even considering suspension. So the difference between a solution and a colloid is whether or not it's transparent. And is fog transparent? Can you see through it? No, you can't see down the road. You can't see through fog. So fog is actually a colloid. It's actually a colloid. So when we make solutions, we are adding a solute to a solvent, and then those two chemicals are dissolving in one another. So the dissolving process requires that solvent particles actually engage in chemical interactions with the molecules of the solute. Okay? And the types of chemical interactions we're talking about are intermolecular forces. So either van der Waals attractions for nonpolar solutions, and stronger things like hydrogen bonding or dipole-dipole forces for polar solutions. Also ion-dipole attractions as well. So here's an example of glucose and water undergoing hydrogen bonding with the water molecules around the glucose molecules. So I obviously haven't drawn all of the hydrogen bonds that these two molecules would have with each other. And then here's an example of an ionic solute dissolving into ions and engaging in ion dipole attractions with the solvent, which is water. So that's how solutions occur. They occur because there are positive, favorable interactions between the solvent and the solute molecules. So just sort of a reminder that solution chemistry is a physical process, not a chemical one. Intermolecular forces are physical forces, just the molecules holding hands. There's no breaking of chemical bonds. There's no creating new substances. It's not a chemical reaction. It's just a physical reaction. So there's some terminology in solution chemistry. So whenever you are making a solution and dissolving a solute into a solvent, that process is referred to as solvation. And if your solvent is water, we often use the term hydration. When we're making an aqueous solution, if we're mixing a solute in water, we are hydrating it. So this chapter also touches on solutions. When you mix a solute in a solvent, for a lot of solutes, there's a limit. There's a limit to how much solute can dissolve in a given solvent. All right, and there's a lot of things that influence that we'll talk about. But a saturated solution is a solution that contains the maximum amount of solute that can dissolve in that solution or in that solvent. So every solution has an equilibrium. It's really a dynamic kind of a situation. It's not just that all the molecules dissolve and then yay, everything's dissolved. What happens is you mix, let's say, salt in water. All right, a lot of that salt is going to solvate. All those ions are going to redistribute and start interacting with water molecules and dissolve. But then there's some other portion of them that will be recrystallizing. So there's a small, if the crystallization process is much slower or much lower than the solvation process, then you have an unsaturated solution. The forward arrow is much faster or much larger than the reverse arrow. When you have a saturated solution, these two rates have equaled out. We've reached an equilibrium state, okay, where the amount that is dissolving in the solution is the same as the amount that's recrystallizing. And here's a picture that I like, okay? So an unsaturated solution, you have little free-floating solute that's all dissolved in solution. And in this saturated solution, you have this, looks like there's a big pile of salt or sugar, whatever the solute is in here. That's because some of it is dissolving, but because it's so saturated, some of it is also recrystallizing. So in a saturated solution, it looks like it's not going into solution at all. It's because that it's dissolving at the same rate that it's recrystallizing. And that's a typical sort of theme with equilibria. It's not that everything comes to a standstill. It's that it appears that there's a standstill. It appears that no more sugar is going into solution. But really, it's more dynamic than that. It's that there's the same amount going into solution as there is coming out of solution. So there's sort of a net effect of nothing going into solution. So saturated solutions can occur in our bodies and cause disease, cause painful conditions. If we build up too much of a solute and we can't, so the body has the kidneys to do most of the work of getting rid of excess solute that our body doesn't need, waste, electrolytes, etc. The kidneys filter it out. If there's a problem with the kidneys, or if we somehow overwhelm our bodies with a certain type of solute, then you can get crystallization of that solute and form either kidney stones, in the second example here, or it can form uric acid crystals, or another type of precipitate that can form in the body that causes gout, which is when uric acid crystals form in soft tissues, mainly in a lot of the joints in the feet and legs. So kidney stones are when calcium, it's usually calcium oxalate or calcium phosphate is the salt crystal that forms when calcium precipitates out of the blood and in the kidneys, which remember are their purpose is where all the electrolytes really go to be filtered out. If there's too much calcium, it can precipitate out with either phosphate or oxalate to form these crystals, which are apparently extremely, extremely painful, depending on their size. But also, if you look at this one, you can see they're not exactly smooth. Salt crystals are never smooth, so you can imagine a crystal sharp, with sharp edges trying to work its way through a small tube in the ureter, then it can be a very painful process. So I mentioned that different factors affect how soluble a solute and is within a solvent, and that is called, so how well a solute can dissolve is called solubility. That's the characteristic. So the two of the traits that we're going to talk about and that are talked about in the chapter are the polarity of the solute and solvent and the temperature of the solvent. Those are two things that can play a big role in how soluble something is, how well two things will go into solution. So first, we're going to talk about the solubility and temperature. Okay, so here's an example. That's sort of a real-world example that you might already know the answer to. So you have a glass of iced tea and a glass of hot tea, and both of these ladies are stirring in, 2 tablespoons of sugar. Which cup of tea is going to dissolve the sugar better, or which one will dissolve it faster? The hot tea, right? Most of us know this, that sugar dissolves better in hot tea or hot coffee rather than cold tea or cold coffee. But it's a little bit different when we're talking about gases in solution. So if you have 2 cans of soda, one is ice cold, one is room temperature, which one is going to lose? So the gas, remember, is the carbon dioxide that's soluble in the liquid. So which soda, I guess the question is, which soda will go flat first? Most of us know the answer in real world, that it's the room temperature soda that goes flat first, right? It loses solubility. That gas goes out of solution faster when the temperature is raised. So the sort of rule that we have here, that is not, there's always exceptions to the rule, but in general, if you are trying to, if your solute is a solid, like sugar or salt, then increasing the temperature increases the solubility, like in the case of the tea, hot tea versus iced tea, and the sugar. If you are a gas, increasing the temperature decreases the solubility, okay? So for solid solutes, increasing temperature increases solubility, and to remember that, try to remember the example of sugar in tea. And for a gas, increasing the temperature decreases the solubility. Okay, and again, think about a can of soda. So, this is just showing you sort of the chemistry of why that is. That at lower temperatures, you have more gas particles dissolved in the liquid portion down here, whereas at higher temperatures, those gas molecules are going to move around even faster, and they're going to escape. They're going to escape the liquid portion, and if you build up enough pressure, you could actually bust open the bottle, which is why you shouldn't leave bottles of soda in your car on a hot day. So there's a scientist named something Henry, his last name was Henry, and he came up with a law, a gas law. There's a whole bunch of gas laws that are named after a whole bunch of different people, and I don't really know what they all did that was so different from each other, that was so special, because a lot of the gas laws seem very similar to me and stem off of a major gas law that we don't go over in the class. But anyway, Henry's law states that the solubility of a gas in a liquid is directly related to the pressure of the gas over the liquid. What does that mean? It means that the more pressure that you put on the gas above the liquid, the more gas will be in the liquid. So you push down on the, this little lever here, you're going to push more gas molecules into the liquid portion. So that's why soda cans and soda bottles are all pressurized. The air in them is pressurized so that there's more carbon dioxide dissolved in the soda. When you open the can or the bottle, you relieve that pressure. The pressure is reduced, and so more gas molecules are free to exit the liquid or the soda portion. So even if you have a bottle of soda, when you open a bottle of soda, you drink half of it, then you close it back up, although the gas particles can't escape from the bottle, there's now a much lower amount of pressure in that airspace. So this isn't soda, but it's a bottle. All right, it's only half full. So this airspace here, if this was carbonated, there's not a high pressure in here. So carbon dioxide from the soda in here could leak out into this airspace. And then when you open the bottle, you release that carbon dioxide. So that's why sodas go flat, reducing the pressure there. It's also how we do gas exchange in the lungs and in the blood. So in Chapter 1, I think we talked about Boyle's law and how we breathe and how differences in pressure, the effect of pressure and volume and how they're related to each other, talking about how we inhale and exhale air into the lungs. Well, Henry's law helps explain how that oxygen in the lungs moves to the blood, and then how the carbon dioxide waste product from the blood moves into the lungs for exhalation. So this has to do with the pressure of each gas in each compartment. So the pressure of oxygen in the lungs is about 160 millimeters of mercury versus the pressure of oxygen in the bloodstream, which is 100 millimeters of mercury. So the pressure in the lungs is higher than the pressure in the blood. Therefore, it's pushing on it. So it's pushing oxygen. The pressure is higher in the lungs, so it pushes oxygen into the bloodstream where the pressure is lower. The converse is true when it comes to carbon dioxide levels. Carbon dioxide levels in the blood are 40 millimeters of mercury, whereas carbon dioxide levels in the lung are 0.3 millimeters of mercury, so much, much lower. So therefore, the flow of carbon dioxide is going to go into the lung. It's going to be pushed from the blood into the lung to be expelled. So that's pretty much how gas exchange works. So a little practice problem, testing your knowledge about solubility generally. Will the solubility of the solute increase or decrease in each of the following situations? A. Sucrose dissolved in water at 95 degrees Celsius instead of 20 degrees Celsius. So, will increasing the temperature increase or decrease the solubility of sucrose in water? It will increase it because it's a solid solute, so increasing the temperature to 95 will increase the solubility. Good. B. A can of soda containing dissolved carbon dioxide is stored at room temperature instead of in the refrigerator. Alright, so in this situation, a warmer situation, warmer temperature, will it increase or decrease the solubility of carbon dioxide in the soda? It will decrease it, right? Because increasing the temperature for a gas solute decreases its solubility. Another sample problem, this one having to do with Henry's law a little bit. Will the pressure of oxygen in the bloodstream increase or decrease in each of the following situations? A. A person climbs a mountain 10,000 feet high where the pressure of oxygen in the air is lower. So the person climbs at the top of this mountain, the pressure of oxygen in the air is lower. So therefore the pressure of oxygen in the lungs, because you're going to breathe in that air, will be lower as well. So then what happens to the pressure in the blood? That's also going to be lowered. If the pressure from the lungs is lower, then there's going to be less pressure pushing oxygen into the lungs. So the pressure of oxygen in the bloodstream will decrease as well. Part B, a person in shock receives mouth-to-mouth resuscitation and the pressure of air in the lungs increases. If you're putting more pressure, according to Henry's law, if you are increasing the pressure of air in the lung, you will then increase the pressure of air in the blood. It's just like this slide here. If we are increasing the pressure of air in the lungs, then we're going to increase the pressure of air in the blood. Okay, so hopefully everyone understands that. So that is solubility and making solutions. Now, when you dissolve a solute into a solvent, there is a chemical equation for that. Chemists have a shorthand way of writing a chemical equation for a solution reaction. So like any chemical equation, the basic chemical equation format is always reactants with a reactant arrow to products. So reactants react to form products. So similarly, we use this format when we're writing solution chemical equations. So, for example, here you have sodium chloride, and you could write sodium chloride plus water or sodium chloride dissolved in water and just write water over the reaction arrow here. Is going to dissolve in water to form sodium ions and chloride ions. Those are the products. So sodium chloride happens to be an ionic compound. And ionic compounds always dissolve to form ions in solution. And since ions conduct electricity, we call these solutes electrolytes. Electrolytes form ions in solution. And ionic compounds always are strong electrolytes. They always dissolve to form ions because that's what they're made of. They're made of ions. They're just two ions stuck together. When you put them in water, those ions dissociate in favor of forming ion dipole attractions with the solvent. Now, some other things to note about this chemical equation. Notice that we've indicated the state here as a solid. The sodium chloride is a solid that we're mixing in water. And the ions now are aqueous because they're part of an aqueous solution in water. So that AQ stands for aqueous. Solutes that do not form ions, so these are going to be covalent compounds. Those are the two different types of compounds, right? Ionic compounds and covalent compounds. So covalent compounds are always going to be non-electrolytes, except for one exception here. The one covalent compound that forms a weak electrolyte are covalent compounds that have a carboxylic acid group. Okay, carboxylic acid group COOH. This one here, the carboxyl group with the oxygen here, and an alcohol coming off of it. This whole thing here is a carboxylic acid group. All right. There's your carboxylic acid group. Those covalent compounds will form some ions in water. I guess we haven't gotten to acids and bases yet, so I'll leave that be. But here are the two ions. A negatively charged, here's the anion and the cation that are formed when carboxylic acids dissolve in water. Now, ionic compounds are considered strong electrolytes because they completely dissociate. So this magnesium, all the magnesium chloride that you put in this solution is going to completely dissolve and disintegrate and dissociate, that's the word, dissociate into magnesium ions and chloride ions. Whereas in a carboxylic acid, not all of the carboxylic acid compounds are going to dissolve. Like, 2% of them or something will actually dissociate into ions. The rest will still be floating around as these intact carboxylic acids. So therefore, they are weak electrolytes because they produce less ions, fewer ions. So I like this picture from your book that sort of demonstrates. So you have an electrolyte solution. In this case, it's a strong electrolyte solution, and you can see the light bulb lights up really bright because when you dissolve magnesium chloride in water, it completely dissociates into ions. So all that's in there now is ions. Whereas when you have a weak electrolyte solution, it weakly conducts electricity. The light bulb is only partially sort of weakly lit up. That's because only some of these carboxylic acid molecules actually dissociated into ions. So in this picture, only one of them, 1 out of 5 molecules, has actually dissociated into ions that can then carry the electric charge. So strong electrolytes are ionic compounds. Weak electrolytes are carboxylic acids. Okay, that's the difference. So, having said that, a little practice problem for you. Predict whether the following will fully dissociate, partially dissociate, or not dissociate when dissolved in solution. So A is sodium nitrate. Sodium nitrate. Is it ionic or covalent? And remember, an ionic bond, referencing your periodic table, is a quick way to determine an ionic bond is it two ions? Is it something from the left side, the metal, plus a non-metal? Okay? And in this case, it's a little bit tricky because you have to know that nitrate is a polyatomic ion, polyatomic anion for that matter. So sodium nitrate is in fact an ionic compound. Okay? So ionic compounds, do they fully dissociate, partially dissociate, or not dissociate in water? They fully dissociate, okay? That means it's a strong electrolyte. Strong electrolytes fully dissociate. So sodium nitrate will fully dissociate, okay? Part B, sucrose. Is it ionic or is it covalent? Sucrose is a covalent compound. It's all carbon, hydrogen, oxygen. These are all nonmetals. So when nonmetals bond with other nonmetals, they have covalent bonds. So this would be a covalent compound. Do covalent compounds fully dissociate, partially dissociate, or not dissociate? They do not dissociate. They are non-electrolytes, and they do not dissociate. Part C, formic acid. The chemical formula is HCOOH. Is it ionic or is it covalent? It is covalent. Again, it's just carbons, hydrogens, and oxygens, which are all nonmetals. So this is covalent, but it does have a carboxylic acid group. COOH is the carboxylic acid group. So will it fully dissociate, partially dissociate, or not dissociate? It will partially dissociate, right? Carboxylic acids are weak electrolytes. They partially dissociate in solution. So hopefully that makes sense, and we'll move on. So when we write these chemical equations for solutions, chemical equations are a lot like math equations, and the reaction arrow can be thought of kind of like an equal sign. And everything on either side of the equation has to equal each other. It has to be balanced. Because according to the law of conservation of mass, you can't create or destroy matter. So you can't mix, you can't, take two things. You can't have an unbalanced equation. I can't think of some kind of layman's example is what I was trying to do. So let's use this diagram here. So for example, magnesium chloride dissolved in water creates magnesium ions and chloride ions, okay? If you look at the picture here, I did like a little clip art picture for you. So a cartoon drawing of magnesium chloride, one magnesium ion, which has a 2+ charge, referencing the periodic table, which I have over my bench over here on my wall. Magnesium has a 2+ charge. Chloride is in group 7, so it has a -1 charge. So magnesium chloride is going to be 1 magnesium plus 2 chloride ions. So when that dissociates, it dissociates into 1 magnesium and 2 chloride ions. So when you can visualize it schematically like this, like in a drawing, I think it's much more obvious, whereas when you're looking at it mathematically, with chemical symbols, it may seem less obvious. So that's why I have this here. But when this magnesium chloride, there's 2 chlorides here. When it dissociates, those 2 chloride ions, that 2 moves out to the front now to indicate that there are 2 ions that are floating free. 2 moles, I guess, of chloride ions is another way. So we don't write the chloride 2 down here. If you write the number as a subscript, that indicates that those molecules are actually bonded together. So in this case, magnesium chloride with a subscript of 2, that indicates that there's a bond there that's bonding those 2 chloride ions together. Whereas on this side here, the 2 in front indicates that there are 2 separate chloride ions floating around. Does that make sense? I hope so. And when you have a number in front, we refer to that as the coefficient. That numbers in front are referred to as coefficients, whereas I guess these numbers are referred to as subscripts. Okay, so this is a table from your book that I think is helpful, sort of the basic recipe for writing a balanced chemical equation. So the first step is to determine whether the substance is a strong electrolyte, a non-electrolyte, or a weak electrolyte, because that's going to determine what the products are that you're writing. So the first thing you do is you're going to write down what the reactant is, and you're going to determine whether it's a strong electrolyte, non-electrolyte, or weak electrolyte. And the way that you do that is by deciding whether they are ionic compounds. So the first thing you're going to ask yourself is this molecule an ionic compound or a covalent compound? If it's an ionic compound, well then you know it's a strong electrolyte. If it's a covalent compound, you have to ask yourself then, is there a carboxylic acid group? If there is a carboxylic acid group, then you have yourself a weak electrolyte. If it's a covalent compound with no carboxylic acid group, then you have yourself a non-electrolyte. Okay? So now you can actually write what the reactants are going to be. You also have to keep in mind about your reaction arrow. So if you have a strong electrolyte or a non-electrolyte, it's a single arrow, because a strong electrolyte completely dissociates and a non-electrolyte completely doesn't dissociate, right? Whereas a weak electrolyte partially dissociates. So it's at a kind of equilibrium. So you have to draw an equilibrium arrow for weak electrolytes to indicate that they're only partially dissociating. Step 3 is to make sure that all of your reactants and products are in the proper phases or states. So for your products, you always want them to be aqueous. And then you start balancing. Then that's when you do the math. So let's work a couple out here, okay? We're going to write a balanced equation for the hydration of the following. Calcium chloride, a strong electrolyte. So this one we don't even have to figure out whether it's a strong or weak or non-electrolyte. It's going ahead and telling us. So it's doing that first step for us. The first step is to determine that, but it's already done for us. So now we need to just write out the equation. And I have this is how I'm going to attempt to do math on the computer because I don't have a smart board. Okay. Let's make this bigger. Guess that didn't really make it bigger. Well, okay, that'll do. So let's start by writing out our reactant here, calcium chloride, which is a solid. Bear with me. You guys should be doing this at home. Get a piece of paper out. Do it yourself. Maybe you want to pause and try it on your own at first, and then play it back and see what the answers are. Maybe you'll even just fast forward through my explanation if you find it, unnecessary. So calcium chloride, we know that it's going to get broken down into, it's a strong electrolyte, so we've drawn a one-way arrow, and it's going to get broken down into calcium ions and chloride ions. All right, the charge on a calcium ion is what? Let's reference our periodic table. It's a group 2, so it's going to have a 2 plus charge. And chloride ion is group 7. It has a -1 charge. All right, and these are our products. So now we need to balance this. Is this balanced? Do we have the same number? What I mean is, do we have the same number of calcium ions, of calcium molecules on each side, and the same number of chlorine molecules on each side? No, we don't. We have 1 calcium on the reactant side and 1 calcium on the product side. Check. But we have 2 chlorides on the reactant side and only 1 chloride on the product side. So we need to double the number here, adding a 2 in front, the 2 coefficient. So now we're balanced. We have 2 chlorides on this side, 2 chlorides on this side, 1 calcium here, 1 calcium there. Our charges are balanced now too, because we have 2 plus charge here, and we have 2 times 1 minus, which means 2 minus charge, so 2 plus 2 minus is 0, so our overall charge is neutral, because the overall charge on this side is neutral as well. So now we are balanced, and I'm now just going to put the finishing touches on it, which are to make sure that we indicate that both of these ions are aqueous in solution. So little AQ, kind of didn't leave enough room for that. Alright, so there's one problem down. Let's go to the next one. CH3OH, this is methanol. It's a non-electrolyte. It's already telling us that, but even if it didn't tell us that, we could figure it out because it's a covalent molecule. It's all nonmetals, and there's no COOH, no carboxylic acid group. So in a non-electrolyte solution, we also CH3. What kind of arrow are we going to draw? A unidirectional one. Okay, one way. Liquid. Alright, and you can also, what else you can do here is write your little, if you want, optional, water here to show that we're dissolving it in water. And you can do the same thing over this arrow. So what is our product going to be? It's a non-electrolyte. It doesn't dissolve. So our product is the same thing with one slight modification. CH3, OH. It is dissolved in water now, even though it has not dissociated. It is dissolved in water, so it is aqueous. So that's the only thing that changes for a non-electrolyte. A chemical equation for a non-electrolyte is it goes from being the liquid or a solid to being aqueous. The last one here, hydrofluoric, this is HF, hydrogen fluoride, or it's actually hydrofluoric acid. And it's telling us that it's a weak electrolyte. This is one that is an exception to some of the rules that we laid out are that if it's a covalent compound, which this is, and it doesn't have a carboxylic acid group, then we would say it's a non-electrolyte. But of course, there's always exceptions to the rule, and this is one. So it's telling us that this is a weak electrolyte. So we need to write this out as a weak electrolyte. So we write out our reactant, HF. These math problems, writing problems are going to take me a little bit longer in this format. That's supposed to be an L for liquid. All right, now what kind of reaction arrow do we write for a weak electrolyte? It's going to be a two-way arrow, an equilibrium arrow, because it only partially is dissociating. What is it partially dissociating into? The two ions. Two ions being that of hydrogen, which has a charge of 1+, and fluoride, which has a charge of, hurry up, what's the charge of fluorine or fluoride? 1-. It's group 7, so it's a 1- charge. Are we balanced? We have one hydrogen on the left side, one hydrogen on the right side, check. One fluoride on the left side, one fluoride on the right side, check. Our charges cancel out, +1, -1. So we are balanced. The only thing left to do is make sure that we note that these are aqueous. Okay? Ooh, cursive might be easier. So that is balanced equations for solutions, all right? Sort of an introduction, I think, to balanced equations. Or have we done it already? I can't remember. I'm giving this lecture before I've done the first half of the class. So balanced equations, making sure you have the same number of each type of atom on either side. Back to the lecture. Let's minimize this. So the next part of the chapter is all about concentrations. And remember I said there's going to be quite a bit of math here. So a little more awkward drawing in Photoshop for me. But hopefully it will be helpful to work these problems out for you guys a little bit. They're really not complicated problems. And they all follow the same basic format. So concentration is just a measurement of how much solute is dissolved in a solution. So concentration is always, the formula for concentration is always amount of solute over the amount of the solution. The thing about concentration is there's a lot of different ways that we can indicate the amount of solute or the amount of solution. There's different units we can use. We can talk about mass, we can talk about volume, we can talk about percentages, okay? So that's where all these different concentration values are going to come into place, just different ways of expressing concentration based on whether we're choosing to use mass or volume or what type of measurement. So some of the different ways to express concentration are as follows. We're going to walk through all of these. You can express concentrations in milliequivalents per liter, which is something that's really only done for electrolytes. And you'll see that milliequivalents per liter or millimoles per liter when looking at electrolyte solutions, particularly like IV solutions. Molarity is moles of solute per liter of solution. I'll go over that definition on a future slide, but molarity is most commonly used in chemistry labs and biology labs in a laboratory and research setting. Is the most common place to see that. I'm not sure you see it so much in healthcare, like in a hospital setting. Percent concentration, there's 3 different ways to express percent concentration that we'll talk about. This is also common for solutions in like IV solutions, like glucose solutions. Alcohol, you buy a beer that's 6% alcohol. Okay, that's the concentration of alcohol in the beer. And parts per million or parts per billion are both forms of concentration that are often used when you're talking about minerals in water, like water treatment, either tap water or testing environmental water for contaminants, oftentimes like heavy metals and things. So, like I said, milliequivalents per liter, or MEQ per L, is often used for electrolytes in body fluids and also in IV fluids. So this just shows you what some typical concentrations of electrolytes are in blood plasma. And notice that the number of milliequivalents of cations equal the number of milliequivalents of anions, so that your positive charges and your negative charges balance out. So you want an overall neutral charge in your body fluids. This is a table from your book showing you the different concentrations in milliequivalents per liter of a lot of different types of IV solutions, intravenous replacement solutions. And notice again here that the positive charges always balance out the minus charges. The milliequivalents of cations is always going to balance out anions. So in the sodium chloride solution, in the potassium chloride solution, it's pretty obvious because it's 1 cation and 1 anion. In these other solutions, if you do the math, if you add up the cations, 147 plus 4 plus 4, it equals 155, which is how many milliequivalents there are of the anions, of the negative charges. So just like in the body, any replacement fluid, you want the charges to be balanced between the cations and anions. Now, for our first math problem, the math is just about unit conversions. We're going from one unit to another. So let's copy this slide over into Photoshop so I can do some drawing. Okay, so here's the problem. A Ringer's solution for IV fluid has concentration of 155 milliequivalents of chlorine. So I'm going to underline this little piece of 100 milliequivalents per liter. All right. If a patient receives 1,250 milliliters of Ringer's solution, how many equivalents of chlorine were given? I like to underline or rewrite out the key sort of numbers in a word problem. I often have to read word problems a couple of times. So the situation here is that somebody was given 1,250 milliliters. So I'll write that out. That's what we're starting with. They were given 1,250 milliliters of this Ringer's solution, which has 155 milliequivalents. Well, I'm going to go ahead and just write it out, and then we'll talk about it. 155 milliequivalents per liter. Okay? Maybe you're getting ahead of me here in the problem. So you can see I've already put the time symbol here because this is a unit conversion problem. We want to go from milliliters, what we've started with, and we're asked how many equivalents. We want to know eventually how many equivalents of chlorine that he received. Okay? Grab my cue here. So if we set this up where we have our starting thing times our conversion factor here of the concentration, 155 milliequivalents per liter. There's just a couple of problems here, and those problems are that the milliliters and liters can't cancel out because they're different units. So we have to convert either milliliters to liters or liters to milliliters. I'm going to choose to go this way, to say that 1 liter is 1,000 milliliters. So instead of writing 1 liter down here, I'm going to turn this into 1,000 milliliters. So now we have units that we can cancel out. Alright? The other option was you could have converted this to liters and said 1.25 liters times 155 milliequivalents per liter. Okay? So now let's just solve this. I'm going to get out my trusty calculator. So 1250 times 155 divided by 1,000 equals 193.75. I'm going to round that to 194. Alright, so that gives us 194, it gives us 194 milliequivalents. But the question is asking us how many equivalents. So how do we convert that to equivalents? How many equivalents are in a milliequivalent? We can I'll write it out separately. Some people might be skilled enough to do this in their head, but I'm just going to write it out. 194 milliequivalents. Alright, and we can look in the back of the book for conversion. 1 milliequivalent is equal to 1,000 equivalents. So how do we write that? We want our milliequivalents on the bottom. Oops, and I said that backwards, by the way. It's 1,000 milliequivalents for 1 equivalent. So 1 equivalent, these take me a long time to write here, is equal to 1,000 milliequivalents. So I'm writing our conversion factor as such. 1 equivalent equal to 1,000 milliequivalents. So now our answer will be in equivalents. 194 divided by 1,000 is 0.194 equivalents. That's how many equivalents of chlorine were given. And that is our answer. And that is like the trickiest type of equivalent problem I will assign, because there were two. Not only did you have to figure out how many equivalents, you had to do a couple of little minor unit conversions so that you could get things to cancel out, like the liters and milliliters. Alright, so make note of that problem. If you didn't copy it down when I was doing it, rewind and copy it, and try to work it on your own. And if you're having trouble, feel free to call me, feel free to email me, and we will set something up. Hopefully I'm still around. Okay, we're going to have a couple more problems to work on as well, so hang on to your hats. Millimoles per liter are very similar to they're basically very similar to milliequivalents per liter. The difference is that milliequivalents per liter take into account the charge of the electrolyte. So if you have 1 mole of sodium ions, it's the same thing as 1 equivalent of sodium ions. 1 millimole of sodium ions, same thing as 1 milliequivalent of sodium ions. That's because sodium has a charge of 1. Calcium has a charge of 2 though. So 1 mole of calcium ions is equal to 2 equivalents of calcium, because equivalents are the same thing as moles, except that it takes into account what the charge is. So whatever the charge is what the equivalency is going to be. That makes sense. So for 1 mole of calcium, you have 2 equivalents of calcium, etc. So just a quick problem here. Using the conversion factors just shown, determine the concentration of a 135 milliequivalent per liter sodium solution in millimoles per liter. Okay, and so let me do this again. Okay, so we have a solution that is 135 milliequivalents per liter, which is a concentration in its own, but it wants to know what the concentration would be in millimoles per liter. So we have milliequivalents per liter, and I guess I should say that this is sodium. Alright, so using the conversion factors we saw on the slide before, how many milliequivalents per millimole? Let's go back here. For sodium, there's 1 equivalent in 1 mole. Or you could also say 1 milliequivalent in 1 millimole, which is what we're going to do. Oh, but I want to do it the other way around. I want the milliequivalents to be on the bottom so they cancel out. 1 milliequivalent, I'm just going to write ME, for every 1 millimole. Alright, and look what happens. Our answer, since our milliequivalents are going to cancel out here, our answer is going to be in millimoles per liter, which is the unit that we are asked for. So it's going to be 135 times 1, so 135 millimoles per liter. Because it's a 1-to-1 ratio, many of you may have been able to do that in your head. 135 milliequivalents per liter is going to be equal to, in the case of sodium, going to be equal to 135 millimoles per liter. Now what if it was calcium? What if it was 135 milliequivalents of calcium? If this was calcium, this is a 2+ charge, then calcium has 2 milliequivalents per millimole. So it would be, what's 135 divided by 2? 67.5 millimoles per liter if it had a 2+ charge. Okay, so hopefully you're kind of understanding that distinction. That's the word I was looking for. So on to molarity. Molarity is another form of concentration, another type of measurement of concentration, and the units of molarity are moles per liter, moles of solute per liter of solution. All right. So, for example, if you are making a glucose solution and you use 5 moles of glucose and 1 liter of solution, then you have, we say it's a 5 molar glucose solution. So molarity is often indicated by that capital M. So 5 moles of glucose per 1 liter of solution would be a 5 molar glucose solution. Okay, and the reason that so when you're using molarity and you're making a solution that has, a certain molarity, the problem with it is in making a solution is that you can't physically count out 5 moles of glucose molecules. It's impossible. It would take you forever, and it's also impossible because you can't see actual moles of glucose. So how do you measure out 5 moles of glucose? Well, you have to do it by weight. And so you can tell how many, you can figure out what the molar mass of glucose is, figure out how much 1 mole of glucose weighs. So then you can weigh out however many moles of glucose you need for your solution. So here's the example problem here. If you're making a 5 molar solution of glucose, first you need to know the molar mass of glucose by adding together the mass of 6 carbon atoms plus 12 hydrogen atoms plus 6 oxygen atoms. So these are the mass of each of those atoms. So 1 mole of glucose weighs 180 grams. 180 grams per mole is the molar mass of glucose. So if we want a 5 molar solution, we need 5 moles. So we need 5 times 180. So therefore, we're going to need 900 grams to mix into that 1 liter to make a 5 molar solution. So molarity problems often have sort of 2 steps because you need to figure out how many grams are in a mole, so then you can figure out how much that number of moles weighs. All right, so here's a practice problem. And again, we're going to transfer over into Photoshop. I think I'm overwhelming my computer a little bit. Don't save, don't save. Nope. Okay. Alrighty. What is the molarity of a solution prepared by dissolving 0.5 moles of sodium chloride in water to give a total of 250 mils? So this is actually a very easy, straightforward one. Let's start by writing what the definition of molarity is. Molarity is what? What's the definition? Hopefully you just said moles of solute per liter of solution. Molarity equals moles. It's going to take me too long. Moles of solute over liters of solution. So moles per liter. Okay? So now we just need to plug in. How many moles of solute do we have? It tells us we have 0.5 moles of sodium chloride being our solute, because it tells us that we're dissolving sodium chloride into water, so we're assuming that that is the solute. That is whatever is getting dissolved into it, that is the solute. So we have 0.5 moles, and that should just say moles. Alright, 0.5 moles divided by how many liters of solution? It says in to give a total volume of 250 milliliters. Well, we do need to have that in liters because that's the proper unit for molarity. So I'm going to do this in my head, but just so you know, there's 1 liter for every 1,000 milliliters. So 250 milliliters is going to be 0.25 liters. All right, 0.25 liters. So then what's 0.5 divided by 0.25? Is 2. I could have done that in my head. So the answer is 2 molar, or you can write 2 moles per liter. The molarity of the solution is 2 molar, 2 moles per liter. That was a fairly easy one. I think I have another one that's a little more challenging. Here we go. All right. How many moles of potassium nitrate are present in 125 milliliters of a 2 molar potassium nitrate solution? All right, so we have 125 milliliters. That's what we're starting with. And the concentration of it is 2 molar, or 2 moles per liter. So 2 moles per liter And we want to know how many moles are in this solution. So we're already set up for that because I guess if I hadn't written it all out first, I could have just written out what we started with. We were starting with milliliters of a solution, and we wanted to know how many moles we had. So we do need some kind of conversion factor that relates moles to volume, moles to liters, and that is the molarity. So we have our conversion factor right here. So 125 milliliters. We do need to be able to cancel out these liters to end up with moles. So I want to convert this to milliliters so that we can cancel it out. So 1 liter is actually 1,000 milliliters. So now I can cancel out milliliters and do the math and end up with how many moles of KNO3. 125 times 2 is 250. Oops. 250 divided by 1,000 is 0.25. So 0.25 moles is the answer to part A. Alright? I'd like you to be trying to do these by yourselves if you can. If not, it's totally fine for me to walk you through them. But if you're feeling confident, you should maybe pause the video and try to do the problem before I walk through it. Then the next question is, how many grams of KNO3 are present? Well, we know how many moles there are of KNO3, and we know that we can calculate the molar mass of KNO3 to get grams per mole, and then we can use that as a conversion factor to figure out how many grams there are. So the first thing I want to do here is add up the molar mass. So potassium has, referring to your periodic table, potassium has a, well, let me write this out first, KNO3. Hopefully you guys are figuring out the molar mass right now. Alright, so the molar mass of KNO3 is potassium, which is 39 grams, plus 1 nitrogen, which is 14 grams, plus 3 oxygens, which are 16 each. So I have a molar mass of 101. 101 grams per mole. Alright, that's molar mass, grams per mole. Alright, so now we have this conversion factor we can use. So we know we're starting with 0.25 moles. Alright, times this conversion factor that we just calculated. So I'll just do like this. Alright, so now we can cancel out our moles, and we're left with grams. Grams of KNO3. So 101 times 0.25 equals 25.25. So I'm just going to say 25 grams of potassium nitrate, KNO3. Okay, so this problem was nice because it kind of broke it down into 2 parts for us. It could have asked us how many grams of KNO3 are present in a 125 milliliters of a 2 molar KNO3 solution. It could have done that. It could have just asked it all in one question. But it was kind of nice and broke it down into 2 different questions so you could do one thing at a time. But some questions might be trickier in the homework where they ask you for grams right off the bat. So you have to do both of these steps in one problem. First, you'll have to figure out how many moles there are, and then you can figure out how many grams there are. Okay? I think the last, well, no, there's 2 more. So percent concentration is another way to express concentration of a solution, and one that's actually used fairly frequently. So it can be expressed in 3 different ways. You can either have mass. Again, so percent concentration, again, it's just a form of concentration. It's amount of solute per amount of solution. And there's 3 different ways you can have it. You can have volume, and you're using either the volume or the mass or both of the solute and the solvent. So you can have percent volume per volume, where it's milliliters of solute per milliliters of solution, times 100% to make it a percentage. You can have percent mass for mass, which is grams of solution over grams of solute over grams of solution. And there's percent mass per volume, which is grams of solute per milliliters of solution. Okay. When you're doing these problems, particularly when it's mass for mass, you'll see this, or if it's volume for volume, don't forget that the solution, the amount of solution is going to be the amount of the solute plus the amount of the solvent. Sometimes they don't tell you the mass of the solution. They'll tell you the mass of the solute and the mass of the solvent, and you have to add them together. So, in fact, we'll do a problem like that right now. So first, starting with the percent mass for mass, which is also sometimes referred to as percent weight for weight. So you might see it written like this in other textbooks or in other places. And I have a problem here that I didn't work out yet. So we'll pull up our trusty Photoshop where I can draw on my slides. Unfortunately, I can't free draw in PowerPoint, so okay, if you have 8 grams of glucose and you mix it with 42 grams of water, what is the concentration in percent weight for weight, or percent mass for mass? And here's a reminder of what the formula is, so let's plug it in. We want to know what this is. This is what we're solving for. Alright, grams of solute. Well, which is the solute, the glucose or the water? The glucose is, okay? Glucose is, the solute is present in smaller amounts. We have less glucose than we do water, so that is the solute. How many grams of solution do we have? Not 42. We have 50 grams of solution, because the solution, remember, is the solute plus the solvent. So I'm going to write 50 grams of solution. All right? All times 100%. And so what does that equal? 8 divided by 50 times 100% is 16%. So in this case, we have made a 16% mass for mass solution of glucose. Easy enough. It's all plug and chug. Just knowing these formulas, and to give you a heads up for the test, these percent mass formulas here, the little basic equation, is in your conversion table. It is on your conversion chart, the one that is included on your tests, the one that's in the back of your book. So you don't need to worry about memorizing them, but you do need to be able to understand them and use them to complete a problem. So percent volume for volume, same thing, except we're talking about milliliters of solute and milliliters of solution as opposed to grams. So one place where you'll see this a lot, in addition to maybe a hospital setting like a 5% glucose, well, actually 5% glucose solution would be a mass per volume probably. Alcoholic beverages often express how the percent alcohol in the solution, and that's a volume per volume measurement. So, for example, a bottle of wine like this Yellowtail that has 14% alcohol, it means that there were 14 milliliters of alcohol in every 100 milliliters of the wine. That comes out to 14%. Okay. There's also percent mass per volume, and that is often used when preparing IV fluids, like I just mentioned, like for a glucose solution or even a sodium chloride solution. and that is also known as percent weight, weight per volume, so mass per volume, weight per volume. So the question I have here is, how would you prepare 1,000 milliliters of a saline solution with a 0.9% sodium chloride mass per volume concentration? So if you had 100 milliliters of solution, we'll plug this number in here, and you want it to be 0.9% sodium chloride, so you plug that number in here, 0.9%. So you're basically solving for X as in grams of solution. So it's 0.9% equals X over 100 times 100. Are you following? I'm not going to write this one out. So both of these 100s are going to cancel out here. Essentially, the answer is going to be 0.9 grams. 0.9 grams of sodium chloride in 100 milliliters of solution would be 0.9% sodium chloride, all right? So try to draw that out. If you have trouble, contact me, contact your classmates. We're going to get through it. So just to note that there's some other related units to mass per volume. So usually here we're in the units for percent mass volume are grams per milliliter. But there are other units for percent mass volume that you might see, grams per deciliter or milligrams per deciliter are similar because it's still mass per volume concentrations. The last one, which I won't focus on a lot of the math of this one, is parts per million and or parts per billion. Those are measurements used for solutes that are in very, very, very teeny amounts. So that are solutions that are very, very dilute. And commonly the ones that come to mind are measuring chemicals in water, namely different minerals, and oftentimes ones that are toxic, so like arsenic levels or something like that in your drinking water. So 1 part per million is 1 milligram per liter, and 1 part per billion is 1 microgram per liter. So these are very small amounts, as opposed to grams per liter. We're talking about milligrams per liter. So here I have one. Do I have just one problem? A couple of percentage problems to practice with. Okay. A lot of math practice. This lecture would normally take me probably 2 classes plus an extra review class, at least 2 to 3 classes with all the math that we're doing. I like to practice math problems with you guys, especially because this is not a math class, there's no math prereq, and everyone kind of is at a different level with their math skills usually. So what is the percent mass for mass concentration of a sodium chloride solution prepared with 60 grams of sodium chloride and 500 grams of water? So again, good thing to start out with is, what is the basic formula? So for percent mass for mass, we're talking about grams of solute over grams of solution. I'm going to just kind of notate this here, try to shorthand. Grams of grams of solute, okay, over grams of solution. Which I'm going to notate like this. So times 100%, of course. Alright, so let's plug and chug. What is our solute? Our solute is going to be the sodium chloride. So we have 60 grams of solute over how many grams of solution? Well, our solution, remember, is both the solute plus the solvent. So it's going to be 560 grams, not 500 grams. Okay, gotta always keep that in mind. The solution is the combination of the two. So times 100%, our answer is what? Hopefully you're ahead of me. 10.7%. 10.7% sodium chloride. Okay? Next one, next problem. Looks like I have 3. How many grams of glucose are present in exactly 500 milliliters of a 5% mass per volume solution? How many grams of glucose are present in exactly 500 milliliters of a 0.5% mass per volume solution? Well, I'm going to plug and chug here. We have a 5% mass per volume. All right. And mass per volume, we're talking grams of solute. In this case, it's glucose. Grams of glucose, which we don't know, it's what it's asking for, over the volume of the solution. It tells us we have 500 milliliters of solution. So 500 milliliters here times 100%. So now we just need to solve for x, our x being that grams of glucose there. Okay, so I'm going to do this. 100 divided by 5 is 20. That's not, sorry, 100 divided by 500 is 0.2. And so we have 0.2 times x now on the right side. And then we multiply both sides, or we divide both sides by 0.2. So 5 divided by 0.2 is 25. The answer is 25 here. All right, so there's a couple ways for you to do that mathematically. Another way to do it is to divide both sides by 100, then multiply both sides by 500. Actually, we can do it that way too. So if you take both sides and divide by 100, then you'll cancel out this one. And 5 divided by 100 is 0.05. Now if we multiply both sides by 500, cancel out this one, you get the same answer. I get 25 grams of glucose. Okay? I'm sorry I can't write it all out. It takes too long, but hopefully you can follow me along verbally. And 25 grams of glucose is how much is in a 5% mass per volume solution of glucose. That's 500 milliliters in volume. Last problem that we'll practice, and then I strongly encourage you to do the in-chapter practice problems as well as all of the end of chapter, do all the homework problems, really get your math down here because they're not difficult, they're not too many steps. What is the concentration in parts per million of a solution that contains 15 milligrams of lead in 100, you know what, I'm gonna skip this one because I don't really concentrate on parts per million. I'm not going to do that for the test. Okay? So that is concentration. How to, bazillion different ways to calculate the concentration of a solution. But it all, remember, it's simpler than, it probably took me 40 minutes to go through those different concentrations and some of the math problems, but really it all boils down to one simple thing. It's amount of solute per amount of solution, period. That's what concentration is. There's just 10 million different ways to determine the amount, but if you're doing amount of solute over amount of solution and you have the right unit, you can do concentration. You can do it. Now, sometimes you have a concentrated solution and you want to dilute it. It's very economical to do things that way. The sort of real-world example in this slide is a can of orange juice concentrate. So I had some limeade the other day, or during the summer, that I didn't read the instructions and I just assumed, like soup, a lot of times soup, it's 1 can of soup and then 1 can of water. So I assumed that limeade was 1 can of limeade and 1 can of water. It was way too strong. It's actually like 3 or 4 cans of water that you're supposed to mix in with it. It's really concentrated, okay? And you don't want to drink it that concentrated. You want to dilute it. So in this, example, we're talking about drinking, but a lot of times in a hospital setting, you need to do dilutions of drugs in order to put them in the right dosage to be able to do dosage information. You need to take a stock solution, a very concentrated bottle of drug, and dilute it in an IV in order to give the right concentration for dosage purposes. So there's a lot of relevance to using dilutions, both that you might use in your real-world life, but also that you would use in a healthcare setting. So in a dilution, the amount of solute that you have usually stays the same. You're just adding solvent to increase the volume, and therefore you're decreasing the concentration. So the math equation for dilutions is this: C initial times V initial equals C final times V final. C being the concentration, V being the volume of the solution. So the initial concentration times the initial volume equals the final concentration times the final volume. I also will sometimes, you'll see me write this as C1 times V1 equals C2 times V2. Okay, so here's an example problem that I'm going to work for you. Okay, so for example, if you have 150 milliliters of a 0.9% saline solution and you dilute it to a final volume of 450 milliliters with water, what is the final concentration going to be? Okay, so here's the first thing I always do is write out the formula, the basic formula, whether it's a concentration problem, a Boyle's Law problem from Chapter 1, or a dilution problem. Okay, if you see the word dilution in the problem, you know it's a dilution problem. We're going to write out CI times VI equals CF times VF. Okay, and then sometimes I just like to make a little table, or you could plug it in right here straight away, what your values are. Okay, so I'm actually just going to do it right here. I'm just going to plug and chug. So we are given 150 milliliters of a 0.9% solution. That's our starting. So let's go ahead and write that in. Our volume is 150 milliliters. That's our V initial, our initial volume. And our initial concentration is 0.9%. 0.9%. And let's see, we have a final volume of 450 milliliters. And it wants to know then what is the final concentration going to be. We've added 300 milliliters. We've diluted it down by adding 300 milliliters of water or something. And so we want to know what this is going to be. So this is just an algebra problem. Now we're solving for x. I'll put in my parentheses. All right. So this question mark here is x. We're solving for x. So I'm going to do 0.9 times 150. 0.9 times 150 is 135. And I'm going to divide both sides by 450. So then if we just divide both sides by 450, that's what I should have done first. All right. Walking you through some of the algebra. Hopefully you are familiar with solving for x and can do this very well. Alright, so cancels out on this side, so we're left with x. We're solving for x now. Plug and chug into the calculator. I get 0.3. 0.3%. Alright, because that's the units that we're left with. This was in milliliters. So our units canceled out here, our milliliters canceled out, and what we're left with is percent. So our answer is 0.3%. Check. Sample problem number 2. Alright, so if you can, if you feel confident enough, I'd love it if you would pause the show right now and attempt to try this one on your own first before I walk you through it. But if you're still a little confused, then we'll do it together. Go ahead and watch. So I already know this is a dilution problem. I haven't read it, but I know that we're talking about dilutions. So I'm already jumping the gun and writing out the formula for a dilution problem, but maybe we should read the problem first. So the problem is hydrocortisone is used as an anti-inflammatory for localized pain. You need to prepare a 50 milligram per ml solution of hydrocortisone for an injection. You have 5 ml of a 200 milligram per ml stock solution of hydrocortisone available. How many milliliters of the 50 milligram milliliter solution can you prepare? So it doesn't, in this problem, it doesn't say the word dilution anywhere, which is something that troubles. Some people have a problem indicating that, identifying a dilution problem without the word dilution. So I've underlined the word stock here. And stock, when you're talking about a stock solution, you're talking about a concentrated solution that you want to dilute down. So the words dilution or dilute or stock solution, those are all going to be keywords that tell you this is a dilution problem. You need to go ahead and write down C1V1 equals C2V2 or CIVI equals CFVF. Okay? So here's our basic solution, our basic equation. Now we just need to plug in the numbers. So what are we starting with initially? We're starting with our concentrated stock solution, right? That's what, if you're making a dilution, you're starting with. So what is our stock solution? We have 5 milliliters of a 200 milligram per ml stock solution. So 5 mils is our starting volume. And our starting concentration is 200 milligrams per ml. Milligrams per ml. And I'll make our little multiplication sign there, okay? Equals our final concentration that we want to have is 50 milligrams per ml. And the question is, what's our final volume going to be? How many milliliters of the solution can we make? Times our x, which is V2. Alright, times V2, that's what we're solving for. Okay, so in order to solve for this, we need to isolate V2, isolate x, so we're going to do that by dividing both sides by 50 milligrams per ml. Alright, 50 milligrams per ml. So it'll cancel out on this side of the equation. But on this side of the equation, 50 milligrams per ml. Alright, so our milligrams per ml unit is going to cancel out. Alright, so we'll be left with milliliters. Our answer will be in the units of milliliters. So now we just have to plug and do the math. So 200 times 5 divided by 50 is 20. So V2, our final volume, is 20 mils. Alright? These are easy. The trickiest part about concentration problems is figuring out which are the starting numbers and which are the final numbers. Some people have a little trouble working that out. And also, if people have really poor algebra skills, they might struggle there too. But remember, on tests, I always give partial credit. If you know the right formula and you write that down and you plug in the numbers correctly and you set it up correctly, but you just struggle and didn't solve for x correctly, I still give partial credit. It's knowing how to set it up. I try to still make it fair for people who are not as strong in their math skills. If they understand how to set up the problem, even if they struggle with solving it. So always remember that to show all your work on your tests, just like I do when I'm doing the problem in class or on virtual lecture. Looks like I have one more sample problem. One more. Oops. Okay. And this one is very similar. How would you prepare? We're talking about preparing a solution. And, in fact, I'm actually not going to do this problem for you. This one is one you should work on your own. How would you prepare 500 milliliters of a 5% mass per volume glucose solution from a 25% mass per volume stock solution? So I'm just going to help you to identify the parts of this problem, and you can do the math on your own. So this is a dilution problem. We have how do we know? Because we have a stock solution that we want to dilute. So our stock solution is going to always be our initial, what we're starting with, okay? So this would be what value in the problem? It would be our initial concentration. It's a concentration, C1, 25% mass per volume. That's a form of concentration. So we have our starting concentration, and it's asking us to prepare 500 milliliters of a 5% glucose solution. That's what it wants us to make. So that's going to be our result, our finals. So this will be our C2 or C final concentration, and our final volume, V2. And it wants to know how we'll prepare it. So essentially, what it wants to know is what volume do we need? What volume of the stock solution do we need to put into 500 mils? Okay. Oh, no, this one's a little bit trickier. Okay, so I will work this with you. Sorry, I just realized that. Okay, so first we need to solve for V1. That's initially what it's asking. So we have C1, I'm not going to write it out, C1 times V1 equals C2 times V2. So I'm going to plug in here. C1 is 25% times V1, which we don't know, equals C2 times V2, C2 being 5%, and V2 being 500 milliliters. Now I remember why I chose this problem. Alright, so solving for V1, our V1 is going to, if we divide both sides by 25%, then we'll get 5 times 50 divided by 25. It's 5 times 500 divided by 25 is going to be 100. 100 milliliters. So our V1 is 100 milliliters. That means we need to take 100 milliliters of the stock solution, dilute it to 500 milliliters by adding 400 milliliters of our solvent, which is probably going to be water. Alright, so it's asking how are you going to make it. It's not asking what is the volume of the stock solution that you need. It's asking how you're going to make it. So you do have to go through this one extra step. You've solved V1, you've found out that you need 100 milliliters of the stock solution, but ultimately you want 500 milliliters of total solution. So you need 100 milliliters of stock solution dissolved or diluted in 400 milliliters of solvent. Alright? Solvent, which is likely going to be H2O. And that is how you would make, that's how you prepare 500 milliliters of a 5% glucose solution. Okay? So we are almost through this lecture. The last part, we're through with all the math in Chapter 7. Yay! Okay? So the point of all of this solution chemistry and understanding the concentrations of solutions, different concentrations, is really to get an understanding of osmosis and diffusion, which is a very important process that goes on in our cells. So cells are all surrounded by cell membranes. A membrane around the cell is a semi-permeable structure. The word semi-permeable means that it allows some chemicals or molecules to pass through, and others are not allowed to pass through. So it's very selective. It's a selectively permeable membrane. And like I mentioned, the body is full of different solutions, full of water. So there are solutions both inside the cell and solutions that are outside the cell, and that membrane is what determines what solute gets to pass through, and water for that matter. Water is actually allowed to freely pass through the membrane, but different solutes are regulated. So the body actually spends a lot of effort trying to maintain all of the body's solutions so that they are what we call isotonic, the same concentration. Iso is a prefix that means same. So the body's trying to keep the concentrations, or at least the electrolyte concentrations within the cell and outside the cell, same. So there's consequences, though, if the concentrations on either side are different. And some examples of how body fluid regulation, if you mess with body fluid regulation, you can die. One example is sort of, I feel like I don't know if famous is the right word, but you ever play those games? You know, what if you were stranded on an island, what foods would you take with you? Things like that. I don't know, I feel like a lot of people get this trivia somewhere that if you're stranded at sea, or like those, random survival skills that you learn that, what's the likelihood you're ever going to use them? I don't know what the likelihood any of you will ever be stranded at sea are, but if you are ever stranded at sea, whatever you do, do not drink the seawater. If you're ever stranded on an island, don't drink the seawater because it will actually dehydrate you faster than if you don't drink any water at all. Why is that? Because there's such a high salt concentration. The salt actually messes with your fluid balance, and we'll see how it does that in a moment, and you can actually become dehydrated. On the flip side of that, drinking excessive amounts of water can also kill you because of the opposite effect. It's not salty enough. Our body, the solutions in our body, most like saline solutions are 0.9% sodium chloride because that is the physiological concentration of our blood. So drinking too much water is too dilute. So you can actually overhydrate yourself and throw off your electrolyte balance. Now, it is very rare and very hard to do, so I wouldn't worry about it if you're someone who you're thinking, oh, I drink a lot of water. Oh my gosh, could I, be overhydrating? Unlikely that you are overhydrating. Especially if you are eating and you are eating foods that contain sodium, then you are fine. But it is possible to overhydrate is the point. And why is that? Why are these different, drinking strategies potentially fatal? It's because of fluid balance and electrolyte balance. So how does fluid balance occur in the body? Well, it occurs through a process, chemistry process called osmosis. And osmosis is a form of diffusion. It's diffusion of water, essentially. And diffusion is any time a molecule moves from an area of high concentration to an area of low concentration. So let me show you the diffusion slide first. Okay? When molecules move from an area of high concentration to an area of low concentration, they just want to distribute themselves more evenly. So here's the sort of example of a couple of drops of food coloring in a glass of water. At first, there will be like, a little spot of green, but it'll slowly sort of diffuse out until, if you don't mix it, even if you don't mix it, a couple hours later you'll come back and all of those green dye particles will be completely distributed. Okay, so osmosis is specifically the diffusion of water. It's the movement of water from an area of high concentration to an area of low concentration. There's actually animation on this slide. So I hope my face is not in the way. Hello. There we go. Okay. So osmosis of water, the movement of water particles from an area of high water concentration to an area of low water concentration. So in this case, it's a little bit confusing semantically, because when we're talking about concentration of a solution, we're talking about the concentration of the solute. Water is almost never the solute, especially in biological systems. Water is always the solvent. So when you say high concentration, a lot of people were thinking about the solute. So another way to say it, which is why I like this slide, is a high solute. It's the movement of water from a low solute concentration to a high solute concentration. Another way to think about it is water is attracted to solute. So water is going to move in the direction of higher solute. It's attracted to the solute. So as is written here, try not to be too confused by the wording, it's the movement of water from a low solute concentration to a high solute concentration, or the movement of water from a high water concentration to a low water concentration. Whichever way is easier for you to think of, it's all correct. Okay, it's just two different ways of stating it. So if one way confuses you, just ignore it. The easiest thing, I think, is to think of water being attracted to solute. So wherever there's more solute, water's going to go. Water's going to try to dilute it. So here's another picture just showing you low solute concentration on this side, high solute concentration on this side. Water is going to move in the direction of the high concentration of solute. Okay? So this, when the water molecules move through a membrane, across a membrane, they exert pressure. They exert a pressure, and that pressure is called osmotic pressure. So the higher the solute concentration, the higher the osmotic pressure is what we call it. So that might be a little bit confusing as well, but think of it, high concentration of solute, high osmotic pressure. Okay, it's going to have a lot of water trying to come into that place. So what are the consequences of osmosis and osmotic pressure on cells? Well, there's a big consequence. So like I said, our body spends a lot of time trying to keep solutions isotonic, where the solution inside the cell is the same concentration as the solution outside the cell. That way the osmotic pressures are balanced and it's a happy sort of place for cells to live. If the solution outside the cell is hypertonic, excessively has more solute, okay, hyper meaning excessive or more than, Okay, if the solution outside the cell has more solute, water is going to want to leave the cells. It's going to go towards the solute, all right, and the cells are going to shrink. They're going to shrivel up and dehydrate. That's what happens in the case of drinking seawater. Drinking salt water would cause this water in your fluids, in your blood fluid, to become excessively salty. So then fluid from your blood cells would then, water from the blood cells would then try to balance that out by flowing out of the blood cell. So don't drink salt water. A hypotonic solution is the opposite situation, where the solution outside the cell in the environment is less concentrated. Okay? In that situation, there's more solute inside the cell, so water is going to move from the environment into the cell, which causes the cells to swell, and in extreme cases can cause them to lyse or explode or, pop, burst. Okay? So in the case of red blood cells, it's called hemolysis. When a red blood cell bursts, it's called hemolysis. When a red blood cell shrivels, it's called crenation. So these are the consequences of not having proper electrolyte balance, fluid balance in red blood cells, but there's other consequences physiologically that you'll learn about in your other classes. So it's important that physiological solutions that in our body are isotonic. So it's important that if you have fluids injected into your body through IV solutions, that they be isotonic to your body solutions, your physiological solutions, in terms of whatever the solute is. So if it's a saline solution, if it's a sodium chloride solution, it should be equivalent to the concentration of sodium chloride in our body, which is 0.9%. If it's a dextrose solution, so is another way of saying glucose, a glucose solution, it should be equivalent to normal blood sugar concentration, which is apparently 5%. Okay, so that's important for our cells, so that it's important for osmosis, so that the cells don't shrivel up or explode because the fluids that you're injecting are not isotonic. Okay? Diffusion is also how we remove waste from our body. So in the kidneys, within the kidneys, diffusion occurs in the nephron, through membranes there. You have waste products in your blood that then enter the nephron, the tubules of the nephron, and because the fluid in the nephron doesn't have those waste, but it's less concentrated. So all of those waste products can then freely diffuse through the membrane. They want to move from an area of high concentration to an area of low concentration within the tubule, and then that's how they get flushed out of the system through the kidneys. If your kidneys are not working properly and not able to excrete your waste, the waste from your blood, you have to go through, either you get a kidney transplant to get some fresh kidneys, or you undergo hemodialysis, which is a process of basically using a machine that does the same thing as the kidney does and filters out the waste from your blood the same way that your kidney does. Essentially, there's lots of waste products in the blood that you're pulling out of your arm, and it goes into this machine that has these dialysis membranes, that has membranes that have similar permeability to that in your body, and it's in a solution. It's bathed in a solution that has a low concentration of those waste particles. So, but actually will have a normal concentration, an isotonic concentration to sodium chloride and dextrose, so that those things won't come out of your blood. But the waste products will, because there will be a higher concentration of waste products in the blood than there will be in this solution. So all the waste products come out, but all the good stuff stays in the blood, like the sodium chloride or the glucose or whatever it is that this dialyzing solution is balanced for. And then the purified blood goes back through the machine and back into a second tube that goes back into your arm. So it pulls out blood, cleans it, and puts it back in, essentially. Okay. So this last problem, I think it's the last. No, I have a couple problems for you here that are just practicing sort of the concept of osmosis and diffusion. Okay. So here's the first one. A cell with a concentration equal to 5% mass per volume glucose is placed in a 10% mass per volume glucose solution. All right, and we have a couple of questions about this. And I just want to draw a picture, because that's what I like to. I'm very visual, personally. So I like to visualize this. So what did he say? We said that the cell has a 5% solution, and it's in an environment here that is 10%. Okay? So now we can visualize this a little bit better. First, we want to know, part A, which direction will water flow to equalize the concentrations? Is it going to flow into the cell or out of the cell? Which way is it going to flow? Water is attracted to solute, remember, so it's gonna flow towards the solution that is higher concentration. So water is going to flow out of the cell. Okay? Which solution is exerting the greater osmotic pressure? The solution with the higher concentration exerts higher osmotic pressure. So that would be the solution outside, the 10% glucose solution. Will the cell swell or crenate? Well, water is exiting the cell. We already decided that in the first part of the problem. So when water moves out of the cell is going to shrink, or in other words, it crenates, right? This one is simply just testing your knowledge about terminology, isotonic, hypotonic, and hypertonic, okay? So the question is, are each of the following solutions considered isotonic, hypotonic, or hypertonic with respect to body fluids? And remember, body fluids are 0.9%. Oh, I guess, well, I shouldn't say. They all have to do with our sodium chloride concentrations, and the physiological concentration of sodium chloride is 0.9%. So I'll just give you that. It's a couple slides back. You should know that. So A, 3% sodium chloride solution. Is that hypertonic, hypotonic, or isotonic to our body solution? It's higher than our physiological solution, which means that it is hypertonic with respect to our body fluids. It's hyper, excessive, higher than our body fluid. Part B, 0.9% sodium chloride solution. That would be isotonic because our body fluids are 0.9% sodium chloride. And lastly, 0.09% sodium chloride solution, hypertonic, hypotonic, or isotonic. That would be hypotonic, less than, because it's less than 0.9%, which is the physiological concentration. Okay? So that is osmosis across membranes. That's how water moves across membranes. In fact, water moves in a very passive way across membranes through osmosis. But remember, we talked about different solutes are selectively, that membranes are selectively permeable to different solutes. So some things are allowed in, but some things are not. Water is allowed in. Water is very small, so it is allowed in. It can freely diffuse by osmosis. But larger molecules or very charged molecules like ions, they have to sort of gain access, like using gated passwords and things like that, if we're going to kind of anthropomorphize a membrane. So the reason that they can't get through is because if you look at a membrane, membranes are composed of phospholipid bilayers, right? It's a phospholipid bilayer. So you've got the polar heads on the outsides, and then the nonpolar tails in the middle here. So how are you supposed, so a large, like polar molecules like glucose, or really charged molecules like ions, they interact well with these polar head groups, but if they try to go through the membrane, they're repelled very heavily by this nonpolar barrier here. So they really can't get through on their own, just passing straight through the membrane. They need some kind of channel or, portal that allows them to go through. Okay, so there's different types of transport across membranes. There's 3 different types that we'll talk about. There's passive transport, where molecules can just freely go through the phospholipid bilayer. They don't need any help, no energy, no proteins or anything. That would be water, would be an example of that. Then there's facilitated transport and there's active transport. Both of these utilize protein channels in the membrane. So passive diffusion, like in the case of water, also in the case of simple gases like oxygen, nitrogen, carbon dioxide, can freely pass through the membrane. There's no energy requirement, etc. Facilitated transport does not require energy, so it doesn't use ATP. When I talk about energy, I mean ATP. Things can just freely pass through, but they need this channel. And this is things that are, these are molecules like I was mentioning, ions, some ions and small molecules that are too charged or too large to fit through the phospholipid bilayer and need some kind of a channel to allow them to pass through. This is still a form of, so we call this facilitated transport. It's still passive in the fact that it doesn't use energy, but it's facilitated by some kind of a protein channel. And an example is a glucose transporter, the glucose transporters that allow glucose into your cells. The last type is active transport. Active transport uses a protein channel, but it also uses energy. It also requires energy. And the thing about active and facilitated, the differences here, the other thing that I should mention about passive transport is it's always movement, it's always diffusion. It's always movement of molecules from an area of high concentration to an area of low concentration. So they want to move down that, we call that a concentration gradient. Okay, they want to move down the gradient. They want to move from the area of high concentration to low concentration. Inactive transport is when you're trying to transport molecules from an area of low concentration to an area of high concentration. You're moving against the gradient. It's like traffic or something. If you have, if it's like you're at school and the bell just rang and everyone's walking down the hallway in one direction, if you're trying to walk in the opposite direction, that's going to be really hard to fight traffic there. So it's going to require more energy. So same thing with molecules that are trying to fight traffic and move against the concentration gradient. It's going to require an input of energy to do that. So these are usually call these pumps. These channels are usually referred to as pumps because they use energy. In other words, ATP. So example here is the potassium hydrogen ATPase, which actually is one of the things that controls stomach acid production. It utilizes active transport. So the last slide here is just a simple test of your knowledge of diffusion and understanding of diffusion. So in this figure here, all right, you have an area of high concentration and an area of low concentration, and you have a membrane, okay, a selectively permeable cell membrane. So in this figure, which direction would passive diffusion occur is the question. Would it occur from right to left or from left to right? It would occur from left to right. Diffusion always occurs. Molecules in an area of high concentration move to an area of low concentration. So diffusion would occur in this direction, okay? And that is chapter 7. That was a lengthy one. I didn't time myself. I still think it was about 2 hours. So again, watch it over again if you need it, or certain parts or certain problems that you need to work through, and email me your questions or call me or come by my office hours if I'm still around campus, because I really want to make sure that you understand this material and read the chapter. I think the book is really well written and good at explaining things where maybe I'm not good at explaining things, and vice versa is what I'm hoping for. So but I don't want you to feel lost just because I'm not in the classroom with you. So please contact me. I'm happy to go over stuff over the phone, or even I could maybe even, if a lot of people are asking questions about the same problems as you're doing homework problems, maybe I could make another video of me working through a couple of the more challenging homework problems and post that. So just let me know if you're having trouble, and I'll stop talking now. The end.